All right, let me make sure we're streaming here. Give me 1 sec to check. Takes it a second to pop up. There we go. All right. So, welcome to the second linguistics lecture video. In this video, we're going to be talking about acoustics, articulation, and feature theory. And just an apology ahead of time, I know the video of me some material in the last linguistics lecture, so sorry about that. I've moved myself to the top right, and I'm hoping that'll do a little bit better. But here we go. Let me just check one more time, make sure things are working. All right. So just to review a little bit, in last week's linguistics lecture, we introduced the class, went over the syllabus, all that boring stuff, and then we learned about the history and kind of broad goals of computational linguistics. So didn't get into any fine-grained details yet last week. Mostly we were just talking about the kind of stuff that would sort of situate you intellectually in terms of where you ought to be at and knowing where the field came from. Then we did a Python lecture last week, right? So if you went and listened to that, right? If you're not a Python expert quite yet, we went into Google Colab and introduced how that worked. We learned how to write a Hello World program in the programming language Python, which is what we're going to be using in this course. And we learned about data types and operators in Python. So in this video, we'll be walking through an introduction to computational phonetics. And there's going to be 3 kind of broad topics we'll cover in that. We're going to talk about acoustic phonetics and how computational tools are used there. We'll talk about articulatory phonetics and how computational techniques are used there. And then we'll talk about feature theory and how some computational simulations have helped us understand that part of the kind of phonetics phonology interface a little bit better. All right, but before we jump into that, I've got something to talk about signed language phonetics. So these slides are going to primarily focus on the phonetics of spoken language, but I want to make sure everyone knows that this isn't because signed languages don't have phonetic properties, right? And I'm using phonetics here in a sort of technical sense, right? You obviously don't hear anything when someone is speaking a sign language, but there are kind of fine-grained ways in which the language of a signed language interacts with the physical world. And there are ways that you can study the visual signal of a sign language. And both of those things that I just described, looking at the kind of data that the language produces and looking at the kind of physical properties of producing that language, that's what phonetics is, the field of phonetics. And sign languages have all the same kinds of structure and complexity that spoken languages have. So they've got phonetics, like I just said, they've got phonology, they've got syntax, they've got all of those things, right? So because of that way, they can be studied, because of that fact, they can be studied in similar ways to spoken languages. So there are phonologists who specialize in sign languages, phonologists or syntacticians that specialize in sign languages, and people who do research on the phonetics of sign language. And that work is good, and I'm not trying to ignore that work in these slides, but there's just not a lot of it out there, and there's even less of that phonetic research on sign languages that deals with computational methods. So that's why we're not going to be talking about the computational phonetics of sign language today. We'll get to talk a little bit about sign language in the next linguistics lecture video. But if you're interested in anything that you feel like I'm leaving out, and you want more resources, feel free to shoot me an email. I'm happy to kind of dig up some stuff of what is out there and share that with you. All right, now let's get started talking about acoustic phonetics. Also, sorry that I take breaks sometimes to drink. That's just part of talking for a long time. So, the study of acoustic phonetics seeks to describe speech using the properties of the sound waves that it's carried in, right? So all waves have 2 properties. They've got wavelength and they've got amplitude. So wavelength is, if you imagine a wave like this, right? A nice simple up and down curvy wave. Wavelength is the distance between one peak of the wave to the other peak, or one trough to another trough, right? the high points or the low points, measure the distance between them. That gives you your wavelength. And if we're talking about like light waves, right, the wavelength determines what color that light is when you're looking at it. The amplitude of a wave is how high the peaks are from the kind of like, from the kind of like base situation or base level of whatever medium the wave is going through, right? You could think of it too as kind of the distance between the peak and the trough, but technically that's not what it's measured from, right? It's measured from this distance. And amplitude, again, if you're thinking of like a light wave, amplitude is like how bright that light is. It's the strength of that light. When we're talking about speech, the wavelength is important mostly because it's going to be proportional to the frequency of the wave. So all sound waves travel at the same speed when they're in air. And when humans perceive the frequency of a sound wave, we call that pitch. And so, sorry, I didn't actually talk about why I was saying all of sound waves travel at the same speed. So because they all travel at the same speed, wavelength and frequency are always just going to be perfectly inversely proportional. So if you know the wavelength of a sound wave, you'll also know its frequency. And frequency is how many of these little bumps, the peaks and the troughs, you get in a particular period of time. So that's frequency, right? Humans perceive frequency as pitch, and pitch is important in all kinds of ways to language. So that's kind of the first thing that is really going to matter to a linguist if we're talking about these sound waves, is the overall pitch of a wave. And what we call that in phonetics usually is F0. So the F0 of an utterance or some segment of speech is just going to be its frequency. How many of these peaks and troughs go by during a certain amount of time on average for the whole segment of speech. The amplitude of a sound's wave, that happens too, right? That's something we also perceive. That's just how loud the sound is, though. So it's how loud someone is speaking in the case of linguistic sound. So now let's talk about actually using some computational methods with these ideas, right? So acoustic phonetics isn't often associated with computational linguistics, but really one of the earliest problems phoneticians had to solve in that realm was very computational in its nature. And it had to do with automatically calculating some important statistics about the sound waves in an utterance. So sound waves are rarely just simple sine waves like the one in that previous slide, or like the one I've got in the top of this figure here. Instead, they're usually more complex, right? So I've got a somewhat complex wave here, that solid line in the bottom of the figure, but speech is even usually more complex than that, right? You may not have ever seen a speech sound wave, but oftentimes they're a line that is seemingly randomly going up and down at a really fast rate sometimes, a really slow rate sometimes, for the full utterance that you're looking at. And it turns out that complex waves like this can actually be broken down into simpler waves. So we call those simpler waves, it's component waves. And what this figure is trying to show you, if you look at the figure as a whole, is how simple waves can be added to 8 more complex waves. So we've got one kind of bigger wave here, and this like smaller wave right below it. And then the third wave on the bottom is meant to be the addition of those 2 waves. So you can see the small bumps kind of ride the larger bumps when you add them together. If you're thinking about this from an actual implementational perspective, like the math you'd have to do here, you would take the y-coordinate at each point in the big wave and the y-coordinate at each point in the small wave and add them together, assuming that anything under the sort of baseline here is negative and anything over it is positive. So you'd add those together and you'd get a wave that looks like this. So what this is called, breaking down a complex wave like this into its component waves, like these guys, is called a Fourier transformation. And it's something that's often done with specialized software because of its complexity. It's also not something that only linguists do. Lots of fields use Fourier transformations. They're very useful in a number of ways. This is just one of their kind of important uses, is breaking down the sound waves that are in speech. Excuse me, I'm about to sneeze. All right, I think it will. No. Okay, it went away. Sorry. Again, I record these live because I don't have kind of the fortitude or the time really to go back and edit the full lecture video. So sometimes little things are going to happen like that. Sometimes I might need to sneeze. All right. So what we call these component sine waves when we're talking about speech especially is formant. The component sine waves, these simple waves here, of a more complex wave, like you might have in speech, are called the speech's formants. The formants are going to be numbered when we're talking about them, and we number them from lower frequencies to higher frequencies. So you can see here these two component waves. This one is has a much higher frequency, and that's because the peaks repeat much more often than they do in the first wave at the top. So if we were to just be breaking this down into these formants, right? This would be formant 1, the one with the lower frequency, and this would be formant 2. Also, formants are going to be the strongest component waves. So you'll actually have like a ton of component waves in any given piece of speech, any piece of acoustic data from speech. You'll have tons and tons of component waves. The formants are going to be the ones with the highest amplitude. So they're the strongest component waves. And so you label them, like I said, from lower to higher frequencies, and these labels are going to use numbers next to the letter F. So we call the overall average frequency of the whole complex wave F0, right? That's what you perceive as pitch, is F0. And what we call these formants is F1, F2, F3, etc. So the frequency is not a formant. F0 is not a formant. But phoneticians just kind of, I think, liked having really similar names to talk about, and so it got a name very similar to the labels that they give to the formants. Another problem for computational phoneticians involves classifying vowels based on their formants. So one of the reasons formants are so important for speech and for understanding speech is that they are essentially how vowels have quality differences. So the difference between the vowel a and the vowel aw, or the vowel o and the vowel e, is primarily a difference between their first and second formant values, their F1 and their F2. And most vowels can be uniquely identified by their F1 and F2 values. And I'm demonstrating that in the image down here on the bottom, the table with the little arrows next to it. Shows all the vowels in English, or at least kind of the main ones. And it shows that the further back in your mouth you make a vowel, the lower the F2 is. The further in the front you make a vowel, and when I say front and back, I mean the position of your tongue specifically. The further in the front you make a vowel, the higher the F2 is. The lower your tongue is when you're making a vowel, the higher the F1 is, and the higher your tongue is when you're making a vowel, the lower the F1 is. So you can take this information and kind of reverse engineer where a person's tongue was, and from that, you'll know what vowel they were creating. But this isn't as easy as it sounds. So it turns out that the specific value given to each vowel that a person is speaking can vary dramatically from speaker to speaker and context to context in terms of what sounds are around that vowel. So I've got here on the right a figure showing the F1 on the x-axis and the F2 on the y-axis for a variety of vowels. This is actually Russian, so that's why the vowels don't match up one-to-one with the English vowels. But each dot is where a speaker's average F1 and F2 were for that vowel in an experiment that was ran like decades ago. This is an older paper I dug up. But what this is meant to show you is just how much speakers can vary. Right? So here you've got the vowel E, and the speakers all kind of agree on what the F1 and F2 should be for the vowel E. But for the vowel O, here, which is here actually, for that vowel, the speakers vary really widely, right? So this O is actually closer to this U than it is to this other speaker's O, right? So it can be really complicated trying to automatically detect what a vowel is, even if you do know it's F1 and F2 automatically, even if you're able to do that Fourier transformation, fine. And this is a kind of problem that phoneticians are trying to solve. So there's two reasons for that. One is to more easily describe the vowel systems of the world in a quantitative way, right? It would be nice if we could go to a community of speakers, record their vowels, and then just automatically know, okay, this language has 5 vowels, they're E, A, A, O, U, or whatever, and this is how the speakers say them, right? It'd be great to just be able to say that about a language and not have to go through months and months of work transcribing all the vowels or looking at the sound waves manually and measuring formants that way, things like that. Another reason for this is to understand how children learn to categorize vowels in their native language. So I pointed out how the O's for these speakers are really varied, right? But if you were to put these people in a room, they wouldn't have any trouble understanding each other talking. Even though the person who is represented by empty circles and the person who's represented by empty squares, even though they have really different pronunciations for the vowel O with very different F1 values, I'm sure they could have a conversation with each other and they wouldn't misunderstand each other's O's. So learning how children learn that kind of categorization that's robust to these differences is also a really important question for computational phoneticians to figure out. And the last thing to talk about with acoustic phonetics and computational tools is the task that phoneticians have of figuring out how children learn to produce the sound waves they hear in their native language. So this is not something that's new, right? Phoneticians have been trying to figure this out as well for a while. But I want to focus in on one recent body of research for this that has shown that a special kind of computational model called a GAN, which stands for Generative Adversarial Network, is particularly well suited for modeling this process. So on the bottom left, I've got a kind of diagram for how a GAN works. So the way this is going to work is it's got two really crucial pieces. One is called a generator and one is called a discriminator. So a generator is going to be taking random noisy input. This doesn't mean noise as in like sounds. This means noise as in like just random static. Just takes a bunch of random input and it's going to map that random input to some audio. So it's going to create a sound wave that depends somewhat on that random input it got. You're also then going to take some audio from a human, some speech data from people saying things. And you're going to give that real human speech data and the generator's audio to a discriminator. The discriminator's job is to tell you whether or not the audio it's given is from a real human or from the generator. And if the discriminator is correct, then an algorithm called backpropagation is used to inform the generator of how it got caught, essentially. So the backpropagation algorithm looks at how the discriminator was able to differentiate between those two audio files and tells the generator, hey, this is kind of what you did wrong. This is the not human-like bit of what you created. If the discriminator is wrong and it accidentally labels the generator's data as human or the human data as generator created, then backpropagation is going to teach the discriminator what it missed. So it's going to say, hey, this was made by the generator, but you thought it was human. Here are all the ways it was different from the human data. And this gets iterated. So this backpropagation algorithm teaches them to be better at their jobs. They do it again, and they're competing with each other. So the generator will get a little better at generating human-like data. The discriminator will get a little better at discriminating between the generator and the humans. And they keep going in a kind of race until you get a generator that's actually really, really human-like. So on the right here of this slide, I've got data generated by a GAN on the left here, and data generated by human on the right. The top of this data is the actual sound wave itself, the raw sound wave. And you can see that those look almost identical. The bottom of these plots is showing you the component sine waves. So the way this is illustrated, I know isn't super intuitive. So you've got this one complex wave, right? And it's being broken down into its component sine waves. And the way that's happening is it's showing you at each frequency what the amplitude of that component sine wave is at a particular point in time. So the lower frequency component sine waves here have very high amplitudes, And you can tell because it's very dark at the bottom. Up here, we've got high frequency component sine waves, and they have high amplitude, at least these kind of bands do. And that's because they have high amplitude, they're showing up as dark because they have high amplitude. Low amplitude would look like the kind of lighter gray. So this is also a way in which the generator is doing a really good job of mimicking the humans. So you can see you've got dark up here, right? So high amplitude component sine waves up towards the top at the beginning of our audio file, and low towards the end of the audio file. And there's even some other details, right? There's like a gap here and a tiny gap there and things like that. So these GAN models have become very, very good models for how children might learn to do this task, right? They are learning to be more and more like a real human in the way that a child is learning to talk more and more like an adult, right? When they're learning their native language. All right, let's move on now to articulatory phonetics. So let's review, and just so you know, I'm doing these reviews not because I think that you all will necessarily need them, but just in case there are people who haven't taken Intro to Linguistics in a while, or who are taking it concurrently with this class, I want to make sure we kind of touch on all the most important things I'm expecting you to remember from Intro to Linguistics. So that's why we've got these review slides in here. So the field of articulatory phonetics studies how people use the different parts of their vocal tract to produce speech sounds. There are a few main parts of the mouth used for talking, so like the lips, the teeth, the tongue. The roof of the mouth is used, and different parts of it are used differently. So you've got the alveolar ridge towards the front, the palate in the middle, and the velum all the way in the back. And then you've got your vocal cords, which I guess aren't really a part of your mouth. They're kind of down below, but they're also obviously very important for speech. Air passes through those vocal cords, and depending on how tightly you have them shut, is either going to pass freely past them or it's going to make them kind of buzz. And then it exits through either the oral or nasal cavity. So the oral cavity is yellow in this image, and the nasal cavity is pink. And the tongue or lips can constrict that airflow in various places to cause the different sounds that appear in the world's languages. Vowels involve less restriction and consonants involve more, for example. That's one way that restrictions can decide what kind of sound you're creating. But there's also differences in those sounds depending on where your tongue is, right? Like I was talking about with the vowels, the position of your tongue changes the formants and the acoustics of your speech. So various methods have been developed to track the way people articulate sounds while speaking. So some of these involve attaching detection devices to articulators like the tongue. So you've got like a little thing attached to your tongue, and it creates an electrical current when it touches a little thing that's attached to the roof of your mouth. And then that can be used to measure how often your tongue is touching the roof of your mouth, or maybe how close it gets to doing that in some cases, depending on how the detectors work. I'm not an expert on exactly the mechanics of those detectors, but they exist, and those are often used. Other methods include like putting some kind of chemical on the roof of your mouth, taking a picture of the roof of your mouth before you say something, then having you say the thing, taking a picture again, and you basically get to see the lines that get drawn there on the roof of your mouth in whatever was put up there. And then the last example here is measuring airflow out of the oral and nasal cavities. So you can wear like a mask that kind of looks like a Darth Vader mask or something, and it measures how much air is coming out of your nose, how much air is coming out of your mouth, and can provide quantitative data on that part of your articulation. But anytime equipment has to be worn by a speaker, or stuff has to be painted on the roof of their mouth or something, there's always a possibility that's going to affect the articulation of the sounds in unnatural ways, right? So because of this, an alternative to these methods is ultrasound imaging. So ultrasounds can be used to record the movement of your articulators without attaching a ton of special equipment to the inside of your mouth or right outside your mouth, right? And the problem with that historically has just been that ultrasounds don't give you easy to analyze quantitative data. So they're just giving you images. They're not giving you specific measurements of airflow or number of times your tongue touches something else or something like that, right? They're just giving you these actual pictures. And if you wanted to know how close the tongue was to the roof of the mouth, you'd have to actually go through and measure each frame in the ultrasound video by hand. But recent work has sought to use computational methods to automate that. So that is a way that a computational technique has had a big effect on articulatory phonetics, because now all of a sudden you don't have to do this data annotation by hand. You can do it automatically, which means that you get way more data and you can tell much more about the way people are articulating their speech sounds. And the last thing I want to talk about in regards to articulatory phonetics is simulating that articulation. So again, just like we talked about how the GAN was a successful model and simulating the creation of the acoustic data that speech involves, there have been simulations as well that specifically want to simulate the articulation involved in speech. And there's various methods for that. The one we're going to kind of zoom into here is called gestural phonology. And it represents sounds numerically by dividing them up into a few gestures. So there is the way your velum moves while making a sound, the way your tongue moves while making that sound, the way your lips move, and the constriction of your vocal folds, which they call the glottal aperture in this figure on the right. And so the way gestural phonology is going to simulate or represent, I guess, in its simulations, these sounds is just over time, how much are you moving those different articulators? How much do you move your velum? How much do you move your tongue or your lips or your glottis? And because it's representing those numerically, it's something that's very easy to translate into a computational domain. So it's very easy to represent these numbers in a computer. And that means that this kind of system can be used and has been used effectively to simulate things like learning sound patterns in a language, right? Instead of having to represent those sounds as phonemes or allophones or bundles of features like you might know about from learning about phonology, you're able to directly represent those sounds as these kind of numerical scores over time that are themselves simulating the articulations made when that sound is produced. All right, so last part of these slides is going to be about feature theory. So again, let's start off with a little bit of a review. Feature theory is the attempt to describe the sounds used in the world's languages by grouping them based on certain characteristics. And these characteristics are often articulatory. Sometimes they also are based on acoustics, though. So I've got down here at the bottom of the slide an incomplete list of the world's consonants. Right here is a lot of consonants, at least a large proportion of the ones used in the world's languages. And you can see that they're grouped, right? So we have palatal sounds, sounds that are made with your palate, right there. We've got velar sounds, sounds that are made with your velum in this column. Nasal sounds are in the second row. Those are sounds in which you're letting air escape through your nasal cavity. So there are all these different kinds of sounds. And originally, linguists wanted to be able to describe these sounds, right? So originally, features, which is what we call these kind of groupings, were just descriptive. They were a way for linguists to describe groups of sounds that often behaved similarly in the world's languages' phonologies and had some kind of phonetic property in common, right? So for example, when you see a phonological pattern, so that is some kind of pattern in the sounds of a language, if you see that applying to M, there's a decent chance if that language has other nasal sounds, so sounds where you're allowing air to escape through the nasal cavity, that language is going to apply that pattern to those as well. Similarly, if you've got a pattern that applies to like P and B, this column here are all the sounds that are made with your lips, bilabial sounds. And if you've got a pattern that applies to P and B, you're probably going to apply that pattern to the other labials in your language as well. And so at first, linguists just wanted to be able to talk about this, right? They wanted to say, oh, this language has this pattern for its labials. That language has that pattern for its nasals, and so on. But quickly, it became a goal of feature theory to also explain why these sounds acted similarly. So were humans born knowing that certain sounds should be categorized in certain ways and just had that as a kind of instinct? Or did they learn those categories when they acquired their native language? And it's because of kind of external factors that languages tend to treat their nasals together and tend to treat their labial sounds as belonging to a group and things like that, right? So is this something that can be explained by an innate instinct, or does it need to be explained by something that's sort of external to the way our brains are programmed? So one approach to feature theory, which is called an innatist approach, assumes that children are born already knowing all of the features they need to represent the sounds in their language. So they already know that nasals go in one group, labials go in one group, palatals go in another group, things like that. And one piece of evidence for this is how humans generalize to novel sounds and combinations of sounds. So a popular example of this generalization I'm talking about is called the Bach test. So I'm not going to pronounce this name perfectly correct, but there's this composer Bach, right? B-A-C-H. And that C-H at the end of his name is pronounced with a velar fricative. So English doesn't really have velar fricatives, but you can take that name and ask an English person to say it, and then ask them to add an S at the end, right? So what would you call a house that belonged to Bach? You'd call it Bach's house, right? You can ask them to say that, and then you can see what exactly they do with that S that's added on to the end. And again, some of this is kind of phonology, so we'll talk more about phonology. We've got plenty of time on phonology in this class. But what I want to focus in on here is that people are able to add that S to the velar fricative, even though they don't have velar fricatives in their native language, right? We don't have those in English. And the reason for this that innatists would claim is that because we already have the features needed to represent the velar fricative. So they're able to handle that sound because they were already born knowing how to group that sound with other velar sounds and all of the other groups it belongs to, right? They have the features to describe it, so there's no problem presented to them when they need to use it and add an S to the end or whatever. So research in the early 2010s wanted to kind of push this idea a little further. So they created computational models of phonological learning that both had and didn't have innate features. So they could make basically the same exact model, but just in one case, give it features, and in another case, don't. Then they could take the generalization of these models to novel data, like the word Bach, and compare that to how humans generalize to that same novel data. So I've got an example of that here on the right. So I've got the model without innate features in this top figure, and the model with innate features on the bottom figure. And in these plots, I know the axis labels aren't quite here for us, but the bottom is showing for each individual point, which represents one of those novel words, how a human felt about that word. So they kind of judged them and told you how good that word sounded. For the y-axis, it's showing you how the model felt about that word. So how good did that word sound to the model? So a perfect match to the human data would just be a perfect line from the bottom left corner to the top right corner. What we can see is that the model without features doesn't do that. It kind of just stays static. So as the human ratings get better, the model just is still kind of the same with all these words. And then you get kind of a steep increase here. So the words that the humans really liked, the model also was really happy with, but it didn't really care before that. This shows the results for the same kind of test, but with the model that had innate features built into it. And you can see that it actually does sort of have a sloping trend here. So as humans liked the words better, the model also liked the words better on average. And so the innatist claim here seems to be supported, right? The model that had features given to it was the model that did better at modeling human data. So it makes you kind of think that, well, maybe these humans also have innate features built into them. However, some recent and not so recent work has suggested that innate features may not be necessary. So this is actually what your reading this week is going to be about. Approaches that assume children learn the features needed to categorize their language as sounds are called emergentist. So this is the opposite of innatist. These are people who think, no, you don't have these features given to you as instincts that you're born with. You kind of just learn what sounds ought to be grouped together. Typically, emergentist approaches fall into one of three camps. So either learning purely from the distribution of the sounds in a language. So that means what sounds are categorized based on what other sounds they tend to appear near, right? So if you're noticing that the sound "b" in your language occurs next to the sound "e" a lot, then that might tell you about something, especially if you see the sound "p" appearing next to "e" a lot, right? If those have a really similar distribution, maybe they need to be grouped together, "b" and "p", that is. The next camp is learning features from the way the phonology uses sounds in a language. So again, we're going to be learning more about phonology next unit. I know that we haven't kind of covered that yet in this class, but phonology is the study of sound patterns in a language. And so one proposal for learning features is, hey, maybe you kind of look at the phonology first and learn that. And then you say, oh, my phonology is using this group of sounds for this pattern. So let's put them in a group together. Let's have a feature label for them. Oh, it's using this other group of sounds. Let's put them in a group together and have a label for them. And then the last camp here, this is actually the camp that your reading assignment falls in, is learning features based on the articulatory and acoustic properties of sounds. So this technique is often the hardest to pull off because you've got to make lots of careful measurements, right? You've got to know all about what the acoustics of a language's sounds are and what the articulations made in a language's sounds are. And we just saw how those are kind of hard to measure, right, in the earlier slides here. But you have to know all of that to kind of understand what kind of data a kid would have when learning the features for their language. So it is difficult, but it probably has the most promise when it comes to modeling human behavior, right? Because you are using all of the information that's available to a child who's trying to learn their first language. So these emergentist models have a lot of explaining to do. They have to explain why humans generalize to novel sounds and groups of sounds in the way that they do. So they have to explain the Bach test and that other kind of more recent research that seems to suggest features are needed. But then they also have to explain why sounds that are featurally similar tend to behave similarly across languages, right? So they have to say, hey, this is why people treat nasals similarly, both in English and in some language that's not at all related to English, right? Things like that. So lots of things that they need to demonstrate, and you'll see in your reading, I think, that they're at least starting to kind of demonstrate some of that and explain some of that. All right, so that's the end of the slideshow for this lecture. Since I was just talking about the reading assignment, let me kind of just note that one more time. I know we talked about this last week, but the reading assignments are real linguistics articles. So you're not reading out of a textbook, you're reading some actual peer-reviewed research, and that's going to come with some difficulties, right? So it will, I'm sure, be pretty hard to try and understand everything that's going on. So you shouldn't try to do that. Try to just read through the article, understanding as much as you can. I would suggest taking notes if you're a kind of note-taking sort of person. And then once you're done with your first pass through it, even if you don't understand it all yet, I would have the article ready, have your notes next to you, and then take the quiz. And the quiz is meant to be a kind of reading guide. So then you can go back and say, oh, okay, this is what Dr. Prickett wanted me to understand about this section in the paper, right? He wanted me to know this. And you'll answer the quiz questions, which I think the questions themselves hopefully aren't too hard to figure out. but they'll kind of guide you in what you're supposed to know when reading the article, what you're supposed to take away from it, and things like that. Because I know a lot of the articles will get a little technical in ways that we really don't want to worry about here in this course. And as always, if you've got any trouble with it, or something about the PDF of the article isn't working or anything like that, definitely let me know. All right, well, I will either see you in the Python lecture video for this week, or I will see you next week. Bye.